Welcome dear learners. We are studying quantum chemistry. In this module, we are discussing the rigid rotator. The discussion consists of two parts and we are focusing part 1. First of all, the module include these things: rigid rotator, a description, Schrodinger wave equation for a rigid rotator, separation of variables, the theta and phi equations, complete solution to phi equation, and normalization. First of all, description of the problem, that is description of rigid rotator. A diatomic molecule rotating about an axis perpendicular to internuclear axis passing through the center of gravity of the molecule constitute an example of a rigid rotator. It is assumed that the internuclear distance does not change during the rotation. Consider HCl as an example. It can be considered as a rigid rotator, provided as a result of the rotation, if there is no shift in the equilibrium distance between hydrogen and chlorine or the equilibrium bond length, if there is no change in the equilibrium bond length, that can be considered as a rigid rotator. Now, the rotation of a diatomic molecule can be described by a rigid rotator. The rigid rotator is like a rotating dumbbell. Consider a system of two masses, M1 and M2, joined by a rigid rod of length small r. Then it is assumed that this dumbbell type geometry rotate about an axis that is perpendicular to the distance r and passes through the center of mass. This situation can be graphically, pictorially represented like this. This is two masses, M1 and M2, separated by the rigid distance small r, that is the sum of R1 and R2. The point that separates R1 from R2 is the center of gravity, and there is an axis which is passing through the center of gravity, and the molecule executes a rotational motion with respect to this axis that is passing through the center of the gravity. And this is the description of the rigid rotator system. Now, moreover, if V1 and V2 are the velocities of the mass M1 and M2 revolving about the axis of rotation, then the total kinetic energy of the rotator is given as kinetic energy capital T is equal to half M1 V1 square plus half M2 V2 square. We know classically the term kinetic energy is equal to half mv square. We are writing this expression analogous to this half mv square. That is, total kinetic energy T is equal to half m1 v1 square plus half m2 v2 square. The linear velocity v is simply equal to angular velocity omega multiplied by the radius of rotation small r. Thus we can write the linear velocity is equal to radius of rotation into angular velocity. That is, v is equal to r into omega. Therefore, m1 v1 square can be represented as m1 into half m1 into r1 omega the whole square and half m2 into r2 omega the whole square. M1 and m2 term appears in the denominator, and that we will get the total kinetic energy like this. Thus we can put T is equal to half m1 r1 omega square, half m2 r2 omega square, or on rearranging we are getting this relation half I omega square, where I is the moment of inertia, I is equal to mu r square, and mu represents the reduced mass of the system. Mu is equal to m1 m2 divided by m1 plus m2, where m1 and m2 are the two masses at the two ends of the dumbbell, or are the two masses of the two atoms present in the diatomic molecule. See, for example, if we are taking hydrogen chloride, mass of hydrogen is taken as m1, mass of chlorine is taken as m2, like that. We have the total kinetic energy, T is equal to half I omega square. But we know the angular momentum of a molecule that execute rotational motion, L is equal to I omega. Incorporating angular momentum, we get kinetic energy T of a rigid rotator. And the expression for kinetic energy is now T is equal to L square divided by 2I, where L is equal to I omega, called angular momentum. Omega represents angular velocity. I represents moment of inertia, that is equal to mu r square. Thus we arrived at the kinetic energy of a rigid rotator equal to L square divided by 2I. Now we are moving on to the Hamiltonian operator corresponding to rigid rotator. We have T is equal to L square by 2I. Since no external force is working on the rotation, the potential energy or potential of the rigid rotator can be set as 0. And we know the fact that the Hamiltonian operator has two components, that is kinetic energy part and potential energy part. And here we know that the potential energy part is equal to 0. Therefore, the Hamiltonian for the rigid diatomic rotator is given as h hat is equal to the first term only, that is h hat is equal to t hat. And we already learned T is equal to L square by 2I. Therefore, T hat is equal to L square hat divided by 2I. 2I is a constant. Therefore, the Hamiltonian operator corresponds to the rigid rotator is given by h hat equal to L square hat divided by 2I. Remember, this is L square hat. L is angular momentum, total angular momentum square operator, that is L square. So, Hamiltonian operator is equal to total angular momentum square operator divided by 2I, and there is no potential energy term in the Hamiltonian operator. Now, spherical polar coordinates. We have the Hamiltonian operator L square hat divided by 2I. We have to express the Hamiltonian operator in terms of spherical polar coordinate rather than using Cartesian coordinate. As we know that systems like particle in a ring, a rigid rotator, etc., Schrodinger wave equation can be conveniently shown in spherical polar coordinate system. The spherical polar coordinate system comprised of three variables, namely r, theta and phi. They are depicted here. The angle theta is called co-altitude, whereas angle phi is called the azimuth. And this about the range of variable and the relation between Cartesian coordinate as well as the spherical polar coordinate. Here, this is a point. It is described as r theta phi or p of x, y, z. The distance from the origin to that point is taken as r, and this is angle theta. That is, angle theta is the angle lies between z axis and the line r. And now you have to consider a plane containing one end is z axis and other end is this line, and that plane makes an angle phi. So, the three variables r, theta and phi are depicted here, and the range of variables are like that: 0 less than or equal to r, 0 less than or equal to phi less than or equal to 2 pi. That is, the range of phi is from 0 to 2 pi. And the last variable, that is the theta, the range of theta is like this: 0 less than or equal to theta less than or equal to pi. From this, it is clear that the range of theta is from 0 to pi and range of phi is from 0 to 2 pi. This about the relation between spherical polar coordinate and Cartesian coordinate. X is given by x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and finally z is equal to r cos theta, and there is no phi function associated with z. This about the relation between spherical polar coordinate and Cartesian coordinate, and now we have to use this spherical polar coordinate to express the Hamiltonian operator for the rigid rotator and to get the Schrodinger wave equation. We have the Hamiltonian of the rigid rotator equal to h hat is equal to L square hat divided by 2I, where L represents angular momentum, L square is angular momentum square, and L square hat is the operator corresponding to square of the angular momentum. If we are switch over from this Cartesian coordinate to spherical polar coordinate, we can first express L square hat, that is square of angular momentum operator, in spherical polar coordinate. And L square hat is equal to minus s cross square into 1 by sin theta dou by dou theta of sin theta into dou by dou theta plus 1 by sin square theta dou square by dou phi square. This about L square, and h hat is equal to L square by 2I. Therefore, I have to divide this L square by 2I to get the Hamiltonian operator. So, the Hamiltonian operator corresponding to rigid rotator is given by s hat equal to minus s cross square by 2I 1 by sin theta dou by dou theta of sin theta into dou by dou theta plus 1 by sin square theta into dou square by dou phi square. This is the Hamiltonian operator corresponds to a rigid rotator from which we can obtain the Schrodinger wave equation for the rigid rotator. Now, we have the Hamiltonian s hat is equal to minus s cross square by 2I 1 by sin theta dou by dou theta sin theta into dou by dou theta plus 1 by sin square theta dou square by dou phi square. The Schrodinger wave equation, as we know, the time independent Schrodinger wave equation, that is Hamiltonian psi is equal to energy into psi. Now we have the value of the Hamiltonian operator in spherical polar coordinate like this, and we have to substitute the value Hamiltonian operator in this expression to get the Schrodinger wave equation for a rigid rotator in spherical polar coordinate. The equation is like this: 1 by 2I minus s cross square 1 by sin theta dou by dou theta sin theta into dou psi by dou theta plus 1 by sin square theta into dou square psi by dou phi square is equal to energy into psi. Or more clearly, the Schrodinger wave equation is like this: 1 by sin theta dou by dou theta sin theta into dou psi by dou theta plus 1 by sin square theta into dou square psi by dou phi square plus 8 pi square I by h square into E psi equal to 0. This one represents the Schrodinger wave equation of a rigid rotator. And it is clear that this Schrodinger wave equation contains two variables. The two variables are theta and phi. Therefore, to get a solution by using this expression is very difficult. And first of all, we have to separate this equation using method of separation of variables. And we are moving on to the solution of the Schrodinger wave equation of the rigid rotator. Now, first part is the separation of variables. We have to adopt the method of separation of variables. We have the Schrodinger equation of rigid rotator as 1 by sin theta dou by dou theta sin theta into dou psi by dou theta plus 1 by sin square theta dou square psi by dou phi square plus 8 pi square I by h square into E psi equal to 0. As I already mentioned, we can see the presence of two variables here. They are nothing but theta and phi, and we have to separate this Schrodinger equation into two component equation, each contain one variable, one with the phi variable and other one with the theta variable. The equation containing theta variable is called theta equation, and the other containing phi variable is called phi equation. We are moving to separate this equation by adopting the method of separation of variables. And for that, the method of separation of variable to be adopted, we have to take an assumption that psi of theta phi, that is the total wave function psi of theta phi, is equal to theta of theta into phi of phi. Note the fact that theta of theta represents the part of the wave function which depends on theta variable only, and phi of phi represents the part of the complete wave function that depends on the angle phi or the variable phi. Thus, the total wave function psi of theta phi is equal to theta of theta into phi of phi. The components on multiplication together to get to the total wave function psi. That is, psi of theta phi is equal to theta of theta into phi of phi, and we have to incorporate this function in the major Schrodinger equation to get the separation. Thus, we have to substitute the value of psi of theta phi is equal to theta of theta into phi of phi in this equation to obtain the separation. That is, we have psi of theta phi is equal to theta of theta into phi of phi. Theta of theta into phi of phi. We have to incorporate the value of psi in this expression. For that, I am putting psi as theta of theta into phi of phi in this expression. Therefore, 1 by sin theta dou by dou theta sin theta into dou by dou theta of theta into phi of phi. This about the first term plus 1 by sin square theta dou square theta of theta into phi of phi divided by dou phi square plus 8 pi square I e by h square into psi. Psi is theta of theta into phi of phi, that is equal to 0. Now, here we can make some corrections. Whenever we are differentiating with respect to theta, phi of phi can be taken as a constant. And whenever we are differentiating with respect to phi, theta of theta can be taken as a constant. If you are taking out that constant, then we get phi of phi divided by sin theta into dou by dou theta sin theta into dou theta by dou theta. This can also be replaced as d theta by d theta because it contains only one variable, plus 1 by sin square theta. Here I can take theta of theta as a constant outside. So this part can be represented as theta of theta by sin square theta into dou square phi divided by dou phi square plus 8 pi square I e by h square into theta of theta into phi of phi is equal to 0. Now, I have to multiply this equation by sin square theta divided by theta of theta into phi of phi. That means I have to multiply each and every term of this equation by sin square theta divided by theta of theta into phi of phi. Whenever I am multiplying this with the first term here, I can multiply here such that phi of phi and this phi of phi will vanish, and sin theta, square theta and sin theta one power will vanish. So the first term will be like this: sin theta by theta of theta into dou by dou theta sin theta into dot theta by dot theta. This about the first part plus the second term. Whenever you are multiplying sin square theta by theta of theta in the second term, sin square theta vanishes and theta of theta also vanishes. So, remaining part will be 1 by phi of phi into dou square phi divided by dou phi square plus this about the second term plus 8 pi square I e by h square dividing by theta of theta term. So, we have to multiply the entire term by sin square theta into theta of theta divided by theta of theta into phi of phi. These two term vanishes and there occur a sin square theta term, sin square theta, and this term will be equal to 0. And on carefully looking, we can see that this equation contain, this part contain the second portion, that is the marked second portion, contain only 5 terms, whereas the first and the third term contain theta terms, such that as a requisite of the method of separation of variable, we have to collect similar terms together, such that I can move the second term to the right hand side. That is, the right hand side will be minus 1 by phi d square phi by d phi square, and the left hand side will be clubbed together. Thus, on rearranging this, I will get this relation sin theta by theta dou by dou theta into sin theta into dou theta by dou theta plus 8 pi square I by h square sin square theta equal to 1 by phi of phi into dou square phi divided by dou phi square. Thus, the left hand side comprised of only theta term and right hand side comprised of phi term. So, we have two parts on RHS and LHS. For the completion of the method of separation of variable, set both the sides of equation 1. See, left hand side and right hand side. Put independently equal to m square. That means left hand side equal to m square and right hand side also equal to m square, such that we can separate RHS from LHS. Thereby we get two differential equations, each in one variable. These equations are the phi equation and theta equation. Thus, what will be the form of the theta equation? Sin theta by theta dou by dou theta sin theta dou theta by dou theta plus 8 pi square I by s square sin square theta is equal to m square. Also, the phi equation m square equal to minus 1 by phi dou square phi divided by dou phi square. Thus, if we equate LHS and RHS separately to m square, we will get two relations. They are the phi equation and theta equation. That is, the phi equation is dou square phi by dou phi square plus m square phi is equal to 0, and the theta equation is 1 by sin theta dou by dou theta sin theta into dou theta by dou theta plus lambda minus m square by sin square theta into theta is equal to 0. This is obtained by slight modification after incorporating a constant term that is called lambda. That is, lambda is equal to 8 pi square I e by h square. So, we got the theta equation and we got the phi equation, and this we got from the method of separation of variable procedure of the original Schrodinger wave equation. Thus, for a rigid rotator, now we have two equations, each in one variable. The first one being the phi equation, that is dou square phi by dou phi square plus m square phi is equal to 0, and the theta equation, that is 1 by sin theta dou by dou theta sin theta into dou theta by dou theta plus lambda minus m square by sin square theta into theta of theta is equal to 0, where lambda is equal to 8 pi square I by h square. These are two equations that we obtained for a rigid rotator problem. Now, we have to discuss the complete solution of the phi equation. We have the phi equation dou square phi by dou phi square plus m square phi is equal to 0. The acceptable solution to this equation is, this is a well-known second order differential equation, which has acceptable mathematical solution that we can adopt from mathematics. That is, the solution is phi of phi equal to n into e raised to plus or minus im phi, where n is depicting the normalization constant. This wave function is acceptable provided m is an integer. M should be an integer. Now, the function phi must be single valued. Also, the function phi of phi is equal to phi of phi plus 2 pi. This is cyclic boundary condition. And because of the fact that the maximum range of phi is up to 2 pi, that is the value of phi ranges from 0 to 2 pi. That means phi at phi is equal to phi at phi plus 2 pi. Also, cos 2 pi m plus I sin 2 pi m is equal to 0. This is valid only if the value of m, which must be an integer, and the value must also be m is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Thus, the acceptable solution to the wave function psi is phi of phi is equal to n into e raised to plus or minus im phi, where m is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. And n depicts the normalization constant. Now, we have to evaluate the normalization constant by invoking the condition of normalization. We have the normalization condition, integral psi star rt, psi of rt, d tau must be equal to 1. For the present system, the integral must be like this. Integral 0 to 2 pi. I am selecting 0 to 2 pi because the fact that the value of the range of phi is from 0 to 2 pi. So, integral 0 to 2 pi, phi star phi d phi must be equal to 1. We have a phi is equal to, or phi of phi is equal to n into e raised to im phi. For convenience, I put plus I. And phi star phi is obtained by taking complex conjugate of phi. In order to get to the complex conjugate, I have to replace I with the minus I. So, phi star phi is equal to n into e raised to minus im phi. We have to substitute the values of phi star phi and phi of phi here, and on integration 0 to 2 pi n into e raised to minus im phi, that is phi star phi, multiplied with n into e raised to plus im phi. This is the value of phi of phi into d phi, and that must be equal to 1. E raised to im phi, e raised to minus im phi vanishes, n into n is equal to n square. So, the result is n square integral 0 to 2 pi d phi. Since integral of d phi is equal to phi and upper limit minus lower limit is equal to 2 pi minus 0, that is equal to 2 pi, I can put n square into 2 pi must be 1. That implies n is equal to 1 by root of 2 pi. Thus, the complete normalized wave function for rigid rotator for the phi equation is phi of phi equal to 1 by root of 2 pi into e raised to im phi. This is the complete normalized wave function. Phi m phi, I am putting m here because phi has a connection with m, where m is equal to 0, plus or minus 1, plus or minus 2, etc. And by putting different values of m here, I will get different values for phi of phi or phi m phi. First few normalized phi of phi values are shown here. If I put m is equal to 0 or modulus of m is equal to 0, then I will get phi 0 is equal to 1 by root of 2 pi, and this one is the real form. Here there are no I forms when m is equal to 0. But if I put m is equal to 1, then there is two chances. There is complex form as well as real form. Real form contain no I parameter, whereas the complex form contain I parameter. This about the complex form and this about the real form. Hence, this table represents first few normalized wave functions of phi m phi, where phi m phi equal to 1 by root of 2 pi into e raised to I m phi, and m is equal to 0 plus or minus 1 plus or minus 2, etc. Thus, by this discussion, we have completed the rigid rotator part 1, and we have completely solved the phi equation, and we studied about the first few normalized functions of the phi equation. That all about the module. Thank you.